So look at the dimension once again. Due to the scaling, okay, W length is becoming L by alpha, width is becoming W by alpha, W into 1 by alpha. T ox oxide thickness is becoming T ox into 1 by beta, and so thereby, okay, now let us consider one by one the different parameters, how they are getting affected by the scaling process. So first consider the gate area, which is a product of length and width, channel length L and channel width W. So both are scaled by 1 by alpha. So thus new gate area, it is becoming 1 by alpha times L, 1 by alpha times W. So compared to the previous, compared to the unscaled version, now gate area is getting reduced by 1, a factor of 1 by alpha square, a factor of 1 by alpha square. Now gate capacitance per unit area, which is usually noted by COX or CO. As we know, COX is a defined as the permittivity of the gate oxide per unit thickness. So epsilon OX by D. D is the thickness of the gate oxide. So as D is scaled by 1 by beta, okay, scaled by 1 by beta, so COX is scaled by a factor of beta. Okay, epsilon OX is a dimensionless quantity. Okay. Now the gate capacitance, formula for gate capacitance CG is epsilon OX by D, or that is COX multiplied by the area of the gate. So COX, as you can see from the last expression, that is scaled by a value of beta. Area, which is nothing but the product of L and W. Each of the L and W is scaled by a factor of 1 over alpha. So the gate area, gate capacitance is changed by a factor of beta by alpha square. Next, so the gate capacitance, that is scaled by a factor of beta by alpha square. Gate capacitance per unit area COX, it is scaled by a value of beta. Gate area, it is scaled by a factor of 1 by alpha square. We will be listing this different parameter in terms of alpha and beta. Parasitic capacitance Cx is given by Ax by D, where D is the depletion width around the source and drain, and which is scaled by usually 1 by alpha. Ax is the area of the depletion region around source or drain, which is scaled by the 1 by alpha square. Its area, so 1 by alpha square. So Cx, parasitic capacitance, is scaled by 1 by alpha square multiplied by alpha, that is 1 by alpha. Carrier density in the channel. Carrier density in the channel is usually quantified by the CO multiplied by VGS. CO is the COX, that is capacitance per unit area. So carrier density per unit area in the on state usually, so is scaled by a value of beta, C0 is scaled by a value of beta, and VGS is scaled by 1 by beta. So QON remains same. Another parameter, channel resistance, on resistance, usually defined as L by W multiplied by 1 by Q1 mu. So mu is the channel carrier mobility and assumed constant to be constant. So RON is scaled by 1. Gate delay is proportional to the product of on resistance and the gate capacitance. So on resistance is scaled by 1 and gate capacitance, as we have derived earlier, it is given by beta by alpha square. So gate delay is scaled by the beta by alpha square. Depending on the value of beta and alpha and their relative values, you can either increased, gate delay is increased, or gate delay may be decreased. You can see this mu C0 by W by L, mu C0 by 2 W by L, the same factor that is here, mu C0 W by L. So this is having the factor of 1 by beta multiplied by VGS minus VT whole square, that is given by the scale factor of 1 by beta. So 1 by beta square term is there, 1 beta square, so 1 by beta is the saturation current scaling. So current density. The cross-sectional area of the channel in the on condition is scaled by 1 by alpha square. So density will be, IDSS is scaled by 1 by beta, so density will be given by beta alpha square by beta. Switching energy, next part, that is Pg equals half Cg into VDD square. We know that already we have derived Cg is scaled by beta by alpha square and VDD is scaled by 1 by beta. So the switching energy per gate, that is defined by 1 by beta alpha square. Power dissipation per gate, it comprises of the static power consumption dissipation and the dynamic component, that is Pg. So total power dissipation Pg is Pgas plus Pgt. So if you look at the static power component, that is given by V square by R, VDD square by R1, and dynamic power component, that is switching energy per gate multiplied by the operating frequency. So if you just elaborate, VDD is scaled by 1 by beta, R1 is 1, so static power is given by 1 by beta square, and Eg scales by 1 by alpha square into beta, if not is alpha square by beta. So the dynamic power also gets scales by 1 by beta square. Therefore Pg is scales by a factor of 1 by beta square. Power dissipation per unit area. So obviously the total power dissipation per area, so it's coming to be alpha square by beta square. Okay. Power speed product, Pt equals Pg multiplied by the time delay. So the factor become 1 by alpha square into beta. Next, this is the final point where the different parameter is This is a list of parameter how they are affected by the scale factor, what we have already derived using the different formulas. Okay, in a snapshot, this is what the supply voltage VDD is usually. Now note here, for constant field scaling and constant voltage scaling, there is no factor of beta. Okay, why? The constant field scaling, we have already mentioned that alpha is equals to beta, whereas for constant voltage scaling, value of beta is 1, so only factor of alpha is remaining there. And constant field scaling, alpha and beta are equal, so you can put always the alpha in place of beta, because alpha and beta are equal. So whatever be the factor of scaling, you are getting the effect only in terms of alpha. Whereas for lateral scaling, there is somewhat different issues, so we may discuss this in some other times. Okay, thank you.